I'm Amin Sheraz Gilani, and I work as a research assistant in IBA under Dr. Gibran Rashid. Um, so we um, so we worked on this problem of quantifying genuine multipartite non-locality of threshold boxes. So these are the co-authors: Peter Hoyer, Gibran Rashid, and me. So now, I'll start off with the basics, like what is non-locality. We've already seen this, but just for a small recap, that if there are many specially separated parties and they share some correlation, some non-local, some correlation which cannot be explained by local principles, by classical physics, then they share a non-local correlation. The simplest example is the PR box, where there are two parties, Alice and Bob, which has two inputs, X and Y, and they get two outputs, A and B, and they share this correlation. So the XOR of A and B is equal to the end of the inputs. So in general, we have these XOR boxes. So we see these XOR boxes like very commonly in the field of non-locality. So I'll So as I said here, that this box does not that this correlation cannot be explained by classical principles. Why is that so? So it is because if we so we have these four conditions in the two-party case that so the first three rows should have an XOR of 0 and the last row should have an XOR of 1. And if we take the XOR of all these rows, I think this should be equal to, then we have a contradiction. So which means that we cannot satisfy all the four rows together. And the most classical, so the best we can do is with probability 3 over 4. How do we represent such a correlation, such a box? We represent it by using a matrix where the columns correspond to the XOR of the outputs and the rows correspond to the inputs. So at 1, 1, the outputs are flipped, and there's a probability matrix. So this one shows that at this input we want this output with certainty. So like this is the very basic version of non-locality. This is bipartite non-locality, and so we just saw this to introduce the idea of non-locality. Now we extend it to multipartite non-locality. So firstly, so I had a phrase of threshold boxes in my title. So firstly, I need to explain that. So before that, let us look at this threshold function where there's a threshold t, and the n parties get input x1 to xn, and the idea is that the Hamming weight. So the Hamming weight is the number of ones. So the number of ones of the input, if they are less than t, then the output should be 0, and if the Hamming weight is at least t, then the output should be 1. So the threshold boxes are the multipartite generalization of the PR box, where on the left hand side of the outputs we take the XOR, and on the right hand side we have this threshold function for t between 0 and n plus 1. So this is how we define the threshold boxes. How do we represent it? As we saw that we can have matrices that specify the threshold boxes, and here are the probabilities. So the columns again represent the XOR of the output, and these represent the Hamming weight. So the rows here represent the Hamming weight. Since we only need the Hamming weight, we don't need the whole input. So we reduce the dimensions, and here we have 1. So the probability should be 1 of outputting a 0 when the threshold is less than t, and the probability should be 1 for outputting a 1 if the threshold is at least t. So we can what do we do is, for quantifying multipartite non-locality, we do need some kind of noise parameter. So how do we introduce noise in these sort of boxes? A simple way is to introduce epsilon noise in each row So at each Hamming weight, we produce the false output with probability epsilon naught, and the correct output with so at row 0 we produce the erroneous output with probability E naught, and the correct output with probability 1 minus E naught, and this we do in all the rows. But then again, we do not allow for arbitrary error. What we want is some conditions on the error. So the error in each row should be bounded by above with some value, with some epsilon. So to reduce the because there's only degree of freedom for one column in this matrix, so we remove the first column, and this is how we represent the threshold box, the threshold T. This is the T here. And again, similar for the noisy case, we again remove the first column, and we have the server box with this condition, as I specify. Now, we would like to simulate this server box, but now what resources do we have? What are we allowed to do? What can we do? So if we have, if we are allowed to do communication between any of the parties, we can simulate this box perfectly, like with zero noise. But here we do not have perfect resources. So what resources do we have? So we have resources such that they are divided between two parties, or between two partitions. So we distribute the parties into two sets, and in those sets they can have arbitrary correlations. So any party in one set cannot have any correlation with any party in the other set. So if we see, for example, here we have specified a bipartition that these parties 0, 4, 3 are in one set, and the rest of the parties in the other set, and there can be no correlation between any of the parties in any of the two sets. So there cannot be intercorrelations between the two sets, which is how we generally define general multipartite non-locality. So this is another example. So if you see this, these are all four-partite correlations. So in this case, if you see that we can partition the parties into 1, 3, and 2, 4, and so this is allowed. So here we can have the fourth party working separately, and the first three parties working together. So this is also allowed. But these kind of correlations are not allowed, where there is at least one link, at least one-way communication between two, where we cannot define two disjoint subsets such that there is no correlation between them. So these are not allowed. So there's some observations to be made before we move further. So if we restrict only to XOR games or the XOR boxes, signaling resources are as powerful as the no signaling resources. And there's a paper by Jason et al. Which proves this, so we can directly use this result. The second observation is that if you want to simulate a symmetric box, so as we saw that the threshold boxes only depend on the Hamming weight of the inputs, which means that they are symmetric. That's the definition of the symmetric functions. So if you have symmetric boxes, we only require symmetric boxes to simulate it, even if we are in lower dimensions. And the third observation is very particular for our case. If you have threshold boxes, so any correlation in this partition where we have n-1 parties are correlated with each other, and there is one separate party. So this kind of partition is at least as powerful as any other partition of this type. So for any arbitrary k. So if you have here n-2, 2, where two parties are separate, and n-k parties work together, and the two parties work together, this would be less powerful than this partition for threshold boxes. So we have this claim for, so this is very specific for our case, for what we want to do. So this means that we only need to, so this means that we have reduced our subspace, and we only need to look at symmetric boxes corresponding to n-1, 1 partition. Okay. Right. So what is our approach? How do we do it? We construct a linear program. So what we do is we just simply minimize the epsilon, the global epsilon, such that the epsilon in each row is less than this epsilon, subject to some conditions. So what are the conditions? The conditions say that the convex combination of the resources allowed, so the ni loops over all the allowed resources. So the convex combination of the allowed resources should at least be able to simulate such a box, which have a global epsilon, which has a global value of epsilon e. And these are two probability constraints, which very trivial probability constraints that has to follow, since we are working in a probability distribution. And so what we do is we find, so in linear programming, there's a theorem called the strong duality theorem, where we just need to find two feasible solutions that are equal, and if they're the primal and dual of each other, then we prove that there is the optimal solution. So this is our dual. The dual contains Bell inequalities. So this Q is a matrix of the dimensions of the matrix of our box, and so this corresponds to Bell inequalities, and these two are again can be associated with a probability distribution. So now this is a snippet of our results. So we see that if we have this sort of a box, so if we have n is equals to 9 and threshold is 6, the boxes we use fall into categories. So the first category contains two boxes, which are the n minus 1 subsets. So here we want output from, so here if we see the perfect box, we want, so here if we see the first n minus 1 rows of the perfect box, we get this box. And if we see it from the bottom, we get this box. So the bottom 4 rows should be 1, and the top 6 rows should be 0. So these are the two corresponding boxes. And the second category is a bit non-trivial. So here we have these sort of boxes that we use for this case. So there is also a pattern here. These are all 1, and at the threshold, so at t minus 1, this is 0, and these are all 1. And now there is a stairwise structure in these boxes. So these are 3 1s, 2 1s, 1 1, and then zeros. And then again, in the upper part, there are 5 1s, 4 1s, 3 1s, 2 1s, and then single. So this is, so we prove that if we use any separable resource, any resource which is not genuinely multipartite non-local, we only need to use these boxes. So these boxes produce the optimal protocol. So we have proven that. And now this is our main theorem. I won't go into too much detail. So this says that the epsilon value is this, n over d, where like it's a bit involved, but I would like to discuss this quantity s. So this quantity s divides. So we have two functions, and the optimal function is the maximum of those two functions, and those two functions are selected based on the sign of this function. And this is just a simple like it's a very beautiful function from combinatorics, where we take this binomial coefficient and we subtract all the binomial coefficients that come after it. This t minus 1, this is from t to n minus 1. And we see if this is positive, then we select the function 1. If this is negative, we select the second function. So these are the asymptotic values. For the end case, if we have the threshold equal to n, we can asymptotically simulate the perfect box with only separable resources. And here in this case, if we have the majority box, we can only do as good as 5 over 6. So this is the probability of the error in the box, the minimum error that we can get. And this is how the function behaves for n is equals to 1000. So now this is some comparison with the results already available. So in the literature, there were already local and quantum bounds for these boxes. Yeah. So if you see, so if you compare the quantum and R bound and the bipartition bound, you may see that for the threshold boxes, the error for the bipartition boxes is less than the quantum than what we get than what we can get using quantum resources, but it is more for the Sweat-Lickney case, the Sweat-Lickney box, for the n-power Sweat-Lickney box. So this means that we cannot compare the quantum resource and the separable classical resource, where each subset is allowed maximum communication, any communication. Yeah. And these are some extensions or future works that I'd like to discuss. So we can generalize our results to all symmetric boxes. So we have done only it for the threshold boxes, but we can do it for all symmetric boxes, or maybe to all XOR boxes. And secondly, we can find the bound after reducing the set of resources further. So so instead of saying that we have two subsets of the parties, if we say that we have M groups, where there is no correlation between any of those groups for any arbitrary M. So what will be the bound in that case? There was one very interesting question that can we find a universal gate set for simulating arbitrary non-local boxes? So this is a very interesting question, but we don't have any progress on it yet. And another one is, what if adaptivity is allowed? Instead of taking the convex combination of the boxes available, we can allow the boxes to work adaptively, such that there's a causal relationship between them. And the last one is that can we recursively construct n-parted boxes from k-parted boxes? And if we can do that, is it better than the direct construction? So we can recursively construct a 5-parted box using a 3-parted box by simulating a 4-parted box, the required 4-parted boxes, and then using those 4-parted boxes to simulate the 5-parted box. So is this doable? The first question would be, and if it is, does it work better than the direct construction? Thank you. Any questions? Yes.
So yeah, you have this table with the majority box and the box. Yeah. Can you explain it again? So this is like you looked at a threshold box.
Yes.
And you try to split the AND box and the majority and the
Yeah. So the end and the majority boxes are the particular cases for the threshold box. So if the threshold is n, we have the end box, the PR box, the multipart PR box, and if you have the threshold n over 2, the floor of n over 2, we have the majority box. So these are very particular cases, and we get the bound to be 0 and 1 over 6 respectively. And using quantum resources distributed over all the parties, we can only do as good as local. But we show that we can do better when we have bipartite resources. But that was not believed to be true, because in the literature, Sweat-Lickney boxes were used as the main source of the multipartite non-locality, and for the Sweat-Lickney case, the error we have for the quantum case is better than the error we get even for the for two subsets. So we tried to negate this conjecture.